live on YouTube.
We are live on TikTok. Yay! Math Thursday, Math Thursday. It's the best day of the week. All right, guys, welcome to Math Thursday. And this week and the whole month of May, we have a sponsor for our Math Thursdays. So if you are interested, we are going to be giving away. We are running a little giveaway for the NumWorks calculator, which is a really cool graphing calculator that I love, that my students love. And so if you're interested, the link is going to be in my profile. So click the link and do the stuff. But yeah, so I'm going to be using the NumWorks calculator. And if you have one, that's great. And so I'll kind of be like throughout the video tonight, just kind of revisiting that a little bit. But welcome to Math Thursday, where we, it's a community. We help you with your math questions. So I know that it's testing season, state testing, SAT is a little bit, a couple weeks ago, but still you may be gearing up for your a placement test or just kind of like getting into finals, right? All of that kind of stuff is upon us. It's that time of year. So any questions that you guys may have, so usually we might mainly focus between like pre-algebra through algebra 2, but of course if you have any more advanced math topic questions, pop them in the chat, and there may be somebody in the crew that can help you out with that. All right, Braden, probabilities. So do you mean just kind of basic probability things, like flipping a coin and things like that, like compound probability sort of stuff? And swimmer 8 in US. Yeah, I can do trig, not really graphing the trig functions, but we can do like basic trig ratios and things like that. All right, so let's start, Braden, with, so probability. Probability boils down to just kind of the overall basic concept of the probability of an outcome. Okay, so the probability of an outcome boils down to the number of ways that it can be favorable, right? And I use the term, even in my classroom, I use the term favorable sort of loosely, like it's kind of like you say it's favorable, but it's just sort of like the one you're paying attention to or desired, right? Or the one that you're kind of talking about, right? So the number of favorable out of the total number possible. So the number of total outcomes, right? So that's what we're looking at. This is what unit we are in real algebra. Oh. So here we've got just this basic of like number of the favorable and the number of total outcomes, right? So let's start with something that everybody kind of always talks about is like a bag of marbles, right? Oh no, I didn't bring it in, shoot. I thought I had my bag of dice with me, but I don't. That's okay. So, well, actually, I can use these dice. Shout out to Dimension 20. Whoop, whoop. Okay. So with these dice here, okay, we have a lot of different things that can happen. Okay. So I've got this D6. I've got this D4. The D4 dice are always so cool to bust out with my students because they're always shocked that, oh yeah, there is a 4-sided die. That's so weird. Okay, so let's say we have this D20. So we have this D20, so it's got 20 sides, and it goes from 1 through 20, okay? So when you roll the dice, right, the number of total outcomes is 20, right? But let's talk about the probability of rolling a 1, 3, or a 5, right? So how many different ways could we roll a 1, 3, or a 5, right? So there's 3 different ways that I could roll a 1, 3, or 5, right? I could roll a 1, I could roll a 3, I could roll a 5. Now, my number of total outcomes would be 20, right? Because there's 20 different things that could happen, right? There's 20 different outcomes that I could have, okay? So if I roll my dice, so 3 out of 20, right? So 3 divided by 20, so that is a 15% chance that I'm going to roll a 1 or 3 or a 5. So let's see. So 15% chance. Let's see. I don't know if I really like those odds, but let's roll it. I got a 2. Dang it. So close. So close. Okay. Now the fact that I rolled a 2, I had a 1 in 20 chance of rolling that 2. So if we did something, if we kind of broadened it, right? If we talked about like, well, maybe instead of 1, 3, or 5, we just say, what's the probability of rolling an even number? Right? Well, in that case, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So my probability of rolling an even number is 10 out of 20, right? I've got 10 even numbers, which is 1/2, which is 50%, right? Okay, so I've got 50%. Let's see. Oh, that time I rolled a 1. Oh man, nat 1, a nat 2, and a nat 1, yikes. I am not in very good shape. Okay, but so that's the basic concept of probability, is that you've got this number of favorable outcomes out of the number of total outcomes, and you look at it as a fraction or a percent. So that's probability in a nutshell, right? Okay. So again, welcome to those of you who are joining. So our Math Thursday is sponsored this month by NumWorks calculators. NumWorks calculators are these really, really cool graphing calculators that I've been using for a couple of years in my classroom. My students really love them. And if you check out my link, there's a link there that we are going to give away a free calculator so you can enter the sweepstakes. Click the link and do the stuff. You can also, these calculators are really intuitive. And so PJ, we don't really do calculus on this channel, but if you have something specific, you can put it in the chat and somebody may be able to help you out with your question. Okay. So on the NumWorks calculator, one of the things that I love, so I'm just going to kind of be revisiting, like every once in a while, we'll be talking about the features that I love about the NumWorks calculator. One of them that I love is that there's actually no difference between the negative sign and the subtraction sign. If I need to do -10, I can just do -10. I know you guys can't see the screen, but I can just use it's the same button. And for those of you who are teaching or learning with a TI with another type of calculator, when there's a different button, you can get kind of mixed up on that and you get a syntax error and all of that. So this makes it really straightforward and really easy to just plug that into your calculator. So again, teachers, I know there's a lot of teachers out there. You can actually get a free sample. So go onto their website and they will send you one for free. Put it in and put in your request. Tell them I sent you. Yeah, so let's get back to our questions. Okay, can you show how to plug back into the equation and get the answer? Let's see. So plug back into the equation and get the answer. I'm not sure. Oh, for quadratics. Okay. So Tyler, do you mean after you factor or if you're trying to find a point on the quadratic equation? So PJ, we're really primarily like pre-algebra through like early pre-calc, really like algebra 2. But if you have a question about abstract algebra, about calculus or anything like that, you can go ahead and just put it in the chat, and there's usually a lot of people in the chat that'll help you out with that. Okay, so a point. So we've got this question about a quadratic. So quadratic functions. Okay, I was actually just teaching this with my students today. Okay, so with a quadratic, okay, if you've got something, we've got this quadratic function. So what makes it a quadratic function is that it's x to the second power. So the fact that it's just to the second power, and that's my highest exponent that I have, that's what makes it a quadratic, okay? Now, in addition to just the x squared, which is just the parent function, we can add and subtract numbers to it to kind of move it all around the grid. We can open it up, we can close it, like we can move it all over the place, okay? So I can do like plus 3x minus 4. Okay, something like that, something really simple, right? So we've got f of x is x squared plus 3x minus 4. This tells us a few things about this quadratic. So first of all, because it's a quadratic, I know that it's going to be a U shape, okay? Now, quadratics go with a parabola. So they're either going to open up or open down, depending on what that a value is. So in this case, this first leading coefficient is a 1. It's positive, so that means that it's opening up. So it's like a cup. You can fill it up. It's opening up because this is positive 1. Okay. Oh, Maddie, this is literally what I'm teaching in my classes right now too. I guess it's the quadratics time of year. Okay. So when we're looking for a point, right? So usually if you're graphing these, right, there's a few things that you would be looking for, okay? So there are a few things that we should be looking for, and one of those things is we've got to be able to find some points, right? Whenever you have, here's a little tip. Whenever you need to graph a line, a function, whatever it is, no matter how complicated this gets, you can always just make a table of values, okay? And it'll give you at least an idea of where the line's gonna go, okay? So f of x equals x squared plus 3x minus 4, okay? So whenever I'm going to plug in a point for that, I would just pick a value for x and you substitute it in, okay? So we're going to go, let's say like f of 1, okay? So what that means is that our x value is 1. Now, everywhere that I have an x, I'm going to substitute it in for, or I'm going to substitute 1 in for x. Okay, so I've got 1 squared. I'm going to actually, I got to practice good habits. So I'm going to put parentheses around the 1. And the parentheses, I mean, for a positive one, it's not as important, but when you have a negative, it's really important to keep those in there. Okay, so I've got 1 squared, which is 1, plus 3 times 1, which is 3, minus 4. So we've got 1 plus 3, which is 4, 4 minus 4, which is 0. So what that means is that when x is 1, y is 0 for this function. So there's a point that I can use to graph my line. Okay, now I can do this with any value. I can always substitute in that function notation. Okay, I could figure out what f of 2 is, right? If x is 2, I'm going to plug it. That's my input. So I'm going to put in 2. So I've got 2 squared plus 3 times 2 minus 4, which is, we've got 4 plus 6, which is 10, minus 4 is 6. So we've got another point here, which is 2, 6. So now we've got 2 of these points for our quadratic equation, okay? So going with that, so this is quadratic functions, right? So going with that, you can then plot some of the points, right? But ultimately, when you're just trying to find a point, okay, you're going to substitute in your x value here, and then you put in your x into here and get what your y value would be, right? Because the function is just, what it's going to do is it's going to take whatever you're putting in, it's going to square it times 3 minus 4. Square it times 3 minus 4. Square it times 3 minus 4. Right? It's going to go on and on. It's just going to do that whole thing every time. Okay? Now, when you are graphing this, okay, this is just, so the question was just about how to find points. Okay? Now, if you need to graph this, okay, if you need to graph this, there are a few things that we would find. I'm going to cover this up just for a minute. Okay. So like I said, Quadratics always have that shape of a U. Okay, now this one is going to open up because it's got a positive first coefficient. If it were negative, it would be opening down. Okay, so here, the first thing that I usually tell my students to find is the vertex. Okay, the vertex, well, if you're looking at a parabola like this, right? The vertex is going to be this point at the bottom. Or obviously, if it's opening down, it would be the point at the top, right? It's the turn. It's the highest or the lowest point on your graph. Okay, so to find that, now, once we find that, or vice versa, we also have this little axis of symmetry. Okay, so a parabola is symmetrical, so we can fold it. Okay, and it folds right along that axis of symmetry, and it goes boop. So what I always tell my students is when you have found one point, you've actually found two because it's a mirror image. Okay, so to find the axis of symmetry and to find the vertex, what you do, so the vertex, the coordinates for the vertex, we use h and k. Okay, now h is the x value, k is the y value. Okay, so to find the value for h, we do negative b over 2a. Okay, when I'm looking at my equation, this is a, which is 1. This is b, which is 3. And this is c, which is negative 4. Okay, so negative b over 2a. So I've got negative 3 over 2 times 1, which is 2. Okay, so we have negative 3 over 2 is our x value of our vertex. This is not a very friendly parabola to graph, but I didn't think about graphing it when I made this one up. That's okay. It is factorable though, so it's friendly for factoring. Okay, but let's go with it, right? So now this is my h value. Okay, so I'm going to change this drawing. The only thing I'm going to change about this drawing is where the axis of symmetry is. Okay, so the axis of symmetry is at negative like 1.5. Okay, just because I know there will be some people that get fussy about this, and it'll be negative 4 and plus 1, something like that. It'll be a little bit, it's a little bit wonky, I'm sorry. It's a little bit wonky, that's okay. Okay, there we go. All right, so now to figure out the k value, let's see, h equals negative b over 2a. Now, if we put the h value in to our equation, that's how we get the k value. So that's how we would get our vertex coordinate. Okay, so f of negative 3 over 2 is going to be negative 3 over 2 squared, yuck, plus 3 times negative 3 over 2 minus 4. Okay. All right, so I can do all of this by hand, but I would also encourage you, shameless plug, to try the NumWorks calculator. They do have an online emulator also if you wanted to play around with that. And it like perfectly matches up with the calculator itself. It's very useful, and their phone app is exactly the calculator too. So what we can do is if we graph this onto our on our calculator, we could also get that, but I'm going to go ahead and I'm just going to do, let's see, negative 3 halves squared plus 3 times negative 3 over 2 minus 4 is negative 6.25. So our vertex, if we might as well just use decimals, that's fine. So our vertex is at negative 1.5 and negative 6.25. So that's where our vertex would be. Now, again, this is kind of, I mean, they're not super ugly decimals, but they're still decimals, which is kind of annoying, but that's okay. All right. Okay, so we've got this vertex here. Okay, so that's where we would find our vertex, and then we can start plugging in for more for more points and things like that. Okay, so if you guys want me to do more graphing quadratics, just pop up in the chat. I would be happy to do more of those. Okay, so again, we're being sponsored this month by NumWorks calculators. If you have a, what in the world? If you have a, if you have any questions about the NumWorks calculators or anything like that, just let me know. Let's see. Okay, you guys want to do more? How to round a square root to the nearest tenth. Well, the ones you have to convert to the other equations. Maddie, do you mean like between like standard and vertex form? So these calculators actually cost less than the other major brands. And if you go on to the NumWorks website, you can find there's all sorts of like discounts and things like that. Again, if you're a teacher, you can ask for a free sample. You can also get a discount code for your students, and I think it's 10 to 15% off that you get, and they will ship it right to your school. So if you have students that need those, yeah. Okay, more vertex and exponential equations. Okay. Oh, that's from last week. Oh my God, that's so loud. I'm sorry. Okay, so more vertex, more quadratics. Okay, so let me do, all right. Tungsten, I teach primarily like Algebra 1, Algebra 2, geometry, a little bit of pre-calc, that kind of thing. Okay, so I'll do quadratics, degrees to radians. Okay, Karina, degrees to radians. Degrees to radians. Leslie, long division, do you mean just long division of numbers or of polynomials? And then I see you asking for a quadratic formula, and I will do quadratics for sure. Okay, we can do a whole bunch of quadratic stuff. Okay, so degrees to radians. Who was it that asked for that? Karina. Okay. Oh man, an electrician by trade. So this math is used. Oh, thank you. This math is used primarily as kind of a foundation for more upper level maths. But even as an electrician, if you're talking about currents and voltage and things like that, it does get into some like quadratic equations and things like that, and kind of currents and voltage and all of that. It's like sine and cosine, things like that, like different wavelengths and things like that. Okay, so degrees to radians. So with degrees to radians, so what a radian actually is, which is something interesting that I had never really taught before this year, but this year I tried teaching it and it does make a lot of sense. So basically you have a circle, okay, and you've got your radius, right? There's your radius. Okay, so usually we have like, we measure circles in degrees, right? We measure circles in 360 degrees. So that's really based on like this measurement, right? You're looking at that distance, that's the degrees, right? Let's say it's like 45 degrees or 40 degrees, okay? So if we say that that's 40 degrees, okay? So when you start learning about trig and the unit circle and things, you start learning about these things called radians, okay? So radians are just a different way of measuring like the measuring a portion of a circle, I guess. But what it is it is where if you take the length of the radius of the circle and you were to fit it around that circle. Okay, so this is one radius length. Okay, So now what they have found is that you can fit the radians around the circle. So a radian is sort of like measuring a portion of a circle, but it's as part of like the part of the circumference. Okay, so it's more like part of the distance around the circle. Okay, so degrees are still kind of looking at the opening between the two legs of the angle. The radians is measuring like this distance with the arc. Okay, so knowing that, okay, all the way around a circle. So all the way around a circle is 360 degrees, right? All the way around a circle this way is also 2 pi radians, okay? So what they, meaning like ancient Greek mathematicians, realized were that you could fit about 6-ish radius lengths around every single circle. Okay, so every single circle, no matter what the radius was, they could fit the same number of radiuses. That's why, I guess that's why they call them radians. Radiuses, that's terrible to say. So they could fit 6 of them. Now, as they did more discoveries, right, they were able to figure out that it was more exactly, it was 2 pi radians, right? So like 6.28 something, right? So 360 degrees is the same thing as 2 pi radians. Okay, so 360 degrees equals 2 pi radians. So if you are converting between degrees and radians, you can use this. This is sort of like a unit rate, right? So 360 is 2 pi. So what that means is that 180 degrees is 1 pi. And that's like a unit rate, right? You have 180 degrees per pi, but you also have 1 pi per 180 degrees. So this is the unit rate that you would use for converting. So if I had, like what we had before was 40 degrees, right? 40 degrees, and I want to figure out how many radians we are talking about, right? I'm going to multiply this by pi over 180. Okay? Now, that's degrees, and with unit rate conversions, right, you want to cancel out the degrees. So the degrees cancel out. So what I'm left with is I've got 40 pi over 180. Now, one thing is that when you have the pi, don't put it into your calculator. It's okay. But you just do 40 divided by 180, and you get this fraction simplified is 2 pi over 9. So 40 degrees is 2 pi over 9 radians. Okay. That's one really fun thing. I know I keep talking about this NumWorks calculator. But it gives you all the answers just as fractions, just as they are. It also simplifies radicals for you. Just saying. It's amazing. Okay. So we've got 2 pi over 9. So now if I'm going from radians back to degrees, I want to get rid of that pi, right? Because there's no pi in degrees. So if I had, 3 pi over 5, and I wanted to convert that back to degrees, okay, I would multiply this by 180 over pi. Because 180 over pi, I know that 180 equals pi, so multiplying it by that is just like multiplying it by 1, so it's still the same thing. The pi's cancel out, and I have 3 times 180 over 5, which is going to give me 108 degrees. And that's my answer. So that's converting between degrees and radians, okay? Very simple, very straightforward. Simple doesn't mean it's not challenging, right? But it is a very simple thing to do, okay? All right, so let's see. So 7th grade, Maddie Gaskar, you are probably going to be doing a lot of solving equations, like 2-step equations. And my recommendation is just practice, 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 practice. That's all I can say about it. Is solving equations, graphing lines, plotting points. Those are going to be your big things. Fractions too. All right, Karina, I'm so glad that I could help you with that. Okay, so quadratic functions. Good. Okay. Differential equations are a little beyond here, but we are going to get into quadratics right now because there are so many of you asking for that. Okay, so we touched on this a little bit earlier, but quadratics, right? So quadratic functions, those of you who have been here for a while, you know I love them. You know I love quadratics, and I will always get into it, okay? All right. Amber, put in your question. I am all about helping out a mom. Okay. All right. So a quadratic, once again, for those of you who may be just tuning in, is based off of this x squared. Okay. That's the parent function. Then from that x squared, we can add in all sorts of things, right? So we could have, x squared plus 5x. Now let me think about, you know what, actually I'm going to do plus 6x minus 2. Wait, hold on, not minus 2. I'm going to do plus 6x minus 7. Yes, okay, that should be pretty friendly for us. Yes, okay, so let's see. So Gianna, I am talking about trinomials right now. So Kobe, I'll add inscribed angles onto our list. We may or may not be able to get to it because we're starting on quadratics right now, and there's quite a bit to go on with that. So Amber, so here's what I would do, actually, to start prepping for the class. If you look at some of the topics, I would just start Googling the topics and see what you can find. Just to kind of watch like review videos and things like that. And if there's a word that you don't understand or a concept that you don't understand or remember, just Google it. Like it's so much, there's so many more resources now than when we were in school the first time around. You've got this. You can always just look stuff up. There are so many resources out there. Even go back onto my videos and check some of the back videos that I've done. I've done a lot of other stuff. Good. I'm glad. Okay. Yep. So we will talk about all of these things. So when you've got this quadratic, okay, the way that a quadratic looks on a graph is a parabola. So we're going to take this quadratic and we are going to go through and we are going to graph it. We are going to solve it. We are going to factor it. We are going to do quadratic formula. We can do completing the square. We can do everything with this same quadratic. Okay. So buckle up. Let's get into it. All right. So we've got x squared plus 6x minus 7. Let's start with graphing it. Okay, because graphing it helps us kind of point out some other things. So any quadratic is going to look like a U shape, right? It's going to open up or it's going to open down. Okay, now this is in standard form. Okay, so standard form, we've got ax squared plus bx plus c. That is the standard form of a quadratic equation. So we're talking about a, b, and c here. These are the coefficients of this function or this equation, okay? So in this case, a is 1, right? Because it's 1x squared. Our b is 6, and our C is -7. Now, when we get to the quadratic formula, we're going to need to know all 3 of these letters because we've got to be able to plug that in, okay? All right, so to find our vertex, which is the point when we're curved, right? It's the bottommost point or it's the topmost point if it's open down, okay? So the vertex, it's like the turn, it's the point. Okay, so the vertex, to find the vertex, what we're going to do, I know we just did this, but that's okay. We're the vertex, the coordinates for the vertex, we use H and K. Okay. To find H, we have -b over 2a. For this quadratic, b is 6, so this is going to be -6 over 2 times a, which is 1, so 2 times 1, which is 2. So our h value is -3. So we have our x value for our vertex, which is -3. Okay. Now what that also means is that is where my axis of symmetry is going to be. So my axis of symmetry is my mirror image line. Okay, so my mirror image line is going to be at -3. So I'm going to go ahead, I like to just kind of sketch this in just so I know, especially when I start plotting points for these quadratics. Okay, so I've got this line just at -3. Now I know my vertex is somewhere along here because I just said my x value is -3. Okay, so my vertex is somewhere along here, so I need to figure out where it is. So I'm going to take that -3 and I'm going to put it back into my original function, just like if I were finding any sort of other point on any kind of, if I were in any kind of, like any other linear equation or any other equation that I was graphing, right? Ooh, H lies and K does tell the truth. We're not at vertex form yet, but that's true. Okay, so we're going to do, let's see, so f of x, so we're going to do f of -3, okay, which is going to be -3 squared. I'm going to put it in parentheses, good habits, right, plus 6 times -3 minus 7. So somebody was asking earlier about function notation and when the input and output is. The input is your x value here. The output is what you get when you plug this all in, okay? So -3 squared is 9. 6 times -3 is -18, right? So I've got 9 plus -18. Oh man, this vertex is going to be really far. Shoot. 3, 6, 9, 12. Oh, dang it. Okay, I'm so sorry. I'm gonna change the C because I want this to be able to use this. So this, we're gonna change it to +8. That should still work just fine. So C is 8. Hasn't changed anything else about our H or anything like that, okay? So it's just going to change where my vertex is going to be. Okay, so this is 9 minus 18 plus 8. So 9 minus 18 plus 8, we've got -1. Okay, great. So that means that my vertex is at -3, -1. That's much better than trying to graph -16. I'm sorry. Okay. Ooh, justo. Polar complex coordinates to regular coordinates or rectangular coordinates, not really the place here, but, well, I'm not really the person to answer that question, but somebody in the chat may be able to help you out because there's often a lot of people in there that can help you out with more advanced calc and pre-calc concepts. Okay, so our vertex is at -3, -1, so my vertex is right here. Okay. There we go. There's my vertex. Boom. All right. So now when I'm graphing, okay, when I look at this, my C value, if it's in standard form, my C value actually tells me my y-intercept. That's my y-intercept is 8. Okay, so I can go ahead and I can graph 8. I go 1, 2, 3, 4, 5, 6, 7, 8. The y-intercept is the y-intercept. It never changes no matter what kind of equation you are graphing. Now, between here and here, there are other points that fall between them, right? And I want to find out what those points are. So let's start with -2. So now I'm just picking a couple more points, okay? I'm picking just a couple more points to help build my curve, okay? So I'm going to choose -2, and the only reason I'm choosing -2 is because it's right next to my vertex. I'm going to keep it easier for myself, okay? So I'm going to do f of -2. So I know my x value will be -2 for this point, okay? So then I've got -2 squared plus 6 times -2 plus 8. So I've got 4 minus 12 plus 8, okay, which is 0. Okay, so I've got -2 and 0. Okay. And then let's go ahead and find f of -1. Why not? It's right there. F of -1. We've got -1 squared plus 6 times -1 plus 8. So we've got 1 minus 6 plus 8, which is 3. Okay, so I've got 3 points here. So I've got -1 and +3 is there. Now, if you notice, I've only done half of this graph, right? I've only got one arm of that parabola going up. Okay, but if you have because it folds, it's an axis of symmetry. If you have found one point, you've actually found 2. Okay? Because this remembers the axis of symmetry, it's going to fold. So all of those points are going to be exact mirror images. So I've got this one here that's 1 away from my axis of symmetry. So I know that this other point is 1 away from the axis of symmetry. Here is 2 away from the axis of symmetry. So I go 2 on the other side of the axis of symmetry. Okay, so it's 3 and 3. So now I've got both sides of my parabola. So now I can do my nice curve. Now I tell my students all the time, it doesn't have to be perfect, but it does have to give, like, it has to be resembling a curve, right? The only thing it can't be is a straight V, because that's an absolute value equation. That's different, right? It's got to be at least a little bit curved. It's not going to be perfect, but it has to be somewhat curvy. Okay, it has to be some gentle curving. Okay, so that is how you would graph a quadratic. Okay, now notice the only thing that I used my calculator for was just to do some of the calculations, right? I don't need a graphing calculator for graphing a quadratic, but it's awfully nice to be able to check it, right? And for those of you watching, right, remember we are sponsored by NumWorks this month. So on the NumWorks calculator, it's so easy to find the zeros and to find the intersections and everything. There's literally buttons where you just go boop, 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 and it finds the zeros for you. There's no setting boundaries left or right. It knows what you want. It knows what you're looking for, and it's amazing. It's such a time saver. You know, with testing coming up, with like standardized tests, like time is time, right? Time is precious. So you've got to be able to go through and be able to efficiently find these different things on here, okay? And they are approved for most every standardized test that I have seen, they've been approved for. There may be, you know, double check, of course, with your testing admins and everything, but they are approved for all of those standardized tests and things like that. Okay. All right. So let's look at so we are still gonna stick with this equation. Now let's talk about solving a quadratic. Okay. So when you're solving a quadratic, what you're really looking for is you are looking for, hi Isaac, you got to be more specific, buddy. What do you want to go over for the exam tomorrow? Okay, so when we're looking for quadratics, when we're looking for solutions to quadratics, what you're really looking for is you're looking for those x-intercepts, okay? So x-intercepts right here are where y equals 0, okay? Where y equals 0. Okay, so Isaac, you want like the word, like the compound interest and stuff like that? So we'll do the compound interest and the exponential growth and decay. Okay. I'll do that after I do this, okay? Okay. So this is where y equals 0. So there's a couple of ways that I can actually solve this. One of the ways that I've been getting most of the questions about that I'll show you guys is using the quadratic formula. Okay, so if we've got f of x, I'm just going to rewrite this function. F of x equals x squared plus 6x plus 8. Okay, now the quadratic formula works for any quadratic that you have. Okay, so even if it can be factorable, which this one can be factored, but we're going to stick with the quadratic formula. So the quadratic formula is, first of all, it needs to be equal to 0 because, remember, keep in mind what we're trying to find, right? We're trying to find these two values for x that are where y equals 0. So I'm going to go ahead and I'm going to put 0 in there. Okay, so I'm going to x squared plus 6x plus 8. Okay. The quadratic formula is, everybody sing it with me, x equals negative b plus or minus the square root of b squared minus 4 or ac all over 2a. Remember, a, b, and c are the coefficients here, right? A is 1, b is 6, c is 8. A is 1, b is 6, c is 8. So now it's just plug them in and solve. Okay? Plug and chug is what we're going to do. So we're going to do negative 6 plus or minus square root of 6 squared minus 4 times 1 times 8 over 2a, which is 2. Okay. So we have negative 6 plus or minus, let's see, 6 squared minus 32 is 4. So the square root of 4 over 2. So now we just keep simplifying and simplifying and simplifying. Okay, so we're going to keep simplifying this. So we've got negative 6 plus or minus root 4. Well, root 4 is 2. So we've got negative 6 plus or minus 2 over 2. So now I've got either negative 6 plus 2 over 2 or negative 6 minus 2 over 2. So negative 6 plus 2 is negative 4 over 2 is going to be negative 2. And negative 6 minus 2 is negative 8 over 2 is negative 4. So these are my two solutions. Okay, so my two solutions would be negative 4 and negative 2. So these are the values for x when y is 0. Okay, so that's one way of solving an equation. Okay, all right. The other way that a few people have asked for is completing the square. So let's talk completing the square, because completing the square is actually what you need to do for writing it in factor or in vertex form also. Okay, so completing the square is when you look at this. Now, completing the square, I don't mess with completing the square unless A is 1 and B is even. If it doesn't meet those requirements, don't complete the square. It's too much trouble. It's way more trouble than it's worth. If you can't factor it and A is not 1 and B is not even, just go to quadratic formula. Just cut your losses. Quadratic formula. It'll work. It'll work. It's fine. Okay? But in this case, A is 1 and B is even, so I can complete the square. Okay? So completing the square means that I'm going to look at this and I'm really just focused on these two bits here. Because x squared plus 6x, okay? Half of 6 is 3. So if I think about this and I look at, okay, so I'm going to try to rewrite this in a way that then I can write it as x plus 3 squared. Because when I can write it as x plus 3 squared, then I can just take the square root of both sides and call it a day, okay? But x plus 3 squared, if I factor that out, right, or if I multiply it out, I have x squared plus 6x. Well, I've got that so far. But then this would be plus 9. Ooh, I don't have plus 9, I have plus 8. But what I can do is I can add 1, right? If I add 1 to that 8, that would give me x squared plus 6x plus 9, which then I could rewrite as x plus 3 squared. But I can't just add 1 to one side, right? I've got to add it to both sides. So what this becomes is, I can just use the orange still, 1 equals x squared plus 6x plus 9. But by adding that 1, I have completed that square. I have made it square, right? So now I've got 1 equals x plus 3 squared. I can square root both sides. And the square root of 1 is going to, so I would square root both sides. So I would do square root of 1 is plus or minus 1. Square root of x plus 3 squared is just x plus 3. So now I've got either x plus 3 equals positive 1, that's one option, or x plus 3 equals negative 1, that's the other option. So now x could be negative 2, or x could be negative 4. And there's the same solutions that I got from my graph. There's the same solutions that I got from my quadratic formula, right? All of that. Now, if you're trying to go from standard to vertex form, okay, you have to complete the square. But then what you do, so after completing the square, you would then, since you have this 1, so you would go 1 equals x plus 3 squared. Okay, you would subtract 1 from both sides. So then you have 0 equals x plus 3 squared minus 1, and that becomes your vertex form. Okay, so if you're trying to write it into vertex form, you have to complete the square first. Same thing if you're trying to do like writing an equation for a circle, you have to do completing the square, right? Those are all things that you have to do, that you have to use completing the square for, okay? All right, so let's shift gears a little bit and we are going to talk about some exponential growth, okay? So exponential is, I don't even want to say it's similar to quadratic, but it can often be confused for quadratic equations because, like I said, quadratics are based off of f of x equals x squared, right? We talked about that. Okay. Exponential equations are based off of 2 to the x. Okay, so exponential equations are where the x is actually the exponent, it's the power. No, we're going to talk about exponential functions. We're not going to get into logarithms right now, but we're just going to be talking about exponential functions. Okay, so an exponential function, generally speaking, looks with a graph, like if we were to take this just like 2 to the x power, right? What it's going to look like is that. Ugh, that was a terrible line. Okay, so this is going to be here. And it's going to start curving. Ah! Oh my gosh, why can I not draw a line tonight? I'm going to go up, and it's going to shoot straight up like that. Now, so that line is going to go whoo, straight up. Okay, and then this line is going to keep going and going. It's going to be getting, oh my God, it's going to be getting closer and closer and closer to 0, but it's not going to cross it. Okay, because a negative exponent, all that does is it flips it down below, like 2. So 2 to the negative 1 power is 1 over 2. 2 to the negative 2 power is 1 over 4. So it kind of keeps cutting it in half and half and half and half. And if you keep cutting it in half, you're never going to get to 0, right? So that line where it never ever crosses is called the asymptote, okay? It's kind of a fun word. I like it. Okay, asymptote. Okay, that's the line that it's always going to be approaching it, but it's never going to actually cross it. Okay, so we can do all sorts of different things to this equation, right? If I did like g of x equals 2 to the x minus 3, right? So, well, if I just did minus 3 here, right? 2 to the x minus 3. So what that would look like is, let's see, so 2 to the 0 power would be 1. Minus 3 is negative 2. There we go. So 2 squared minus 3 is negative 1. 2, so that's 8. That's 5. Wait. Oh, yeah, squared. Oh, my gosh. 1 cubed, that's 5 to the 4th. That's not going to show up. Okay. Now, in this case, this minus 3, now that is my asymptote. Okay. This is now the line that it's not going to cross. Okay. So my line is going to go here. My exponential equation is going to go here, and then it's going to go, woo, it's going to go straight up like that. Okay, so it's going to be generally like the same kind of curve, and then it's going to go straight up. It's just going to be not crossing that asymptote at negative 3. Okay. All right, so when is this useful? Exponential growth and decay is the most common time when you use this. Okay, so when you're just looking at an exponential growth, so one of the most common things is like if you have a, I don't know, there's a lot of times where the question will be something like a population growth, right? So like a population of animals is, we start with 150 animals, and then it's going to increase, right? The population is going to increase by 15% every year, okay? So if it increases by 15% every single year, how many after, I don't know, 30 years? No, let's do 20 years. Okay, so there's all of our key information, right? It's 150. We're starting with 150. It's increasing by 15%, and after 20 years, how much will it be increased? Okay, now I can't just figure out what 15% of 150 is and add it every year, right? Because 150, let's see. So after 1 year, if it's increasing by 15%, let's see. So I'm going to have like 173 after 1 year. So then I wouldn't be adding in another 15% of 150. I would be adding in another 15% of 173. Okay, so that's the thing about exponential growth, is that it builds up. So it's not just 15% of 150 every single time. It's 15% of 150, then 15% of that, then 15% of that. So it's going to go bigger and bigger and bigger, a lot faster. Okay? So the way that I would figure this out is the time is going to be my exponent. Okay? So in this case, I've got my, well, really any like growth equation. I'm going to have my starting population or my starting amount, my starting whatever it is. Where am I starting? For growth, I'm going to multiply that by 1 plus my percent as a decimal. And then my exponent is going to be my number of years or my amount of time, right? If they say it's by months, then it's however many months, right? It depends on how much it's increasing or like how often it's increasing, right? Okay, so in this case, I would be looking at 150 times 1 plus 0.15, and then it would be to the 20th power. Okay, the reason I'm adding that 1 is because it's increasing, so it's 150. This is sort of like, I always think of this as like the yes and, right? It's like the improv equation, basically. It's like you're taking that 150, that 1, and we're adding 15%, right? Okay. So there's no way I can do this in my head. So I'm going to do 1 plus point, calm down, 0.15 to the 20th power. Holy moly, this is a population explosion. We're going to have about 2,455 animals, whatever it is. That is a great population growth, right? Okay. I am a high school teacher. I taught middle school for a long time, but I am a high school teacher now. Okay, so now. Wait, what? Oh no, hold on. I got my little, why are you still there? Oh, what? Which of these objects has strings? I can't see that. Oh my gosh. Like, I can't even see what these are.
Which object has strings?
It says, which of these objects is used for headwear? What?
What?
It looks like spaceships. Can you see it?
Hold on. Oh my god.
Guys, sorry, I've got like an inactivity thing that's going on that it's like, usually it's pretty easy. It's like, just drag this puzzle piece over.
There's 2 hats. There's one in the middle.
That one?
Yeah. Yep.
Okay.
And then the one in, yep, that one.
Oh my god, those look like flying saucers. Jeez Louise. Okay, sorry about that.
So easy.
Okay, so would you include a decimal if you get a decimal? Yes. So I would include a decimal if this were money or if it said to the nearest tenth or something like that. In this case, like, I think I set it up as like a population. So like you wouldn't have a decimal of an animal, but yeah. So you would have, like, you would just round it off to whatever makes the most sense, right? Now, if it were something like 150 decreasing, so this 150 decreases by 15% after 20 years, what would it be? Okay, so in this case, since it's a decreasing, it's start times 1 minus the percent. So this is going to be 1 minus 0.15 to the 20th. So everything else stays the same. The only thing is that since it's a decreasing, it's minus. So now I've got 150 times 1 minus 0.15 to the 20th. Whew! It's going to be 5.8. So that's a pretty big decrease, right? But I mean, that's after 20 years, but still. So it's never going to fully get to 0. right? Because again, we looked at that exponential growth, right? It's going to hit that asymptote. It's never going to hit 0, right? But it's going to get closer and closer and closer. Okay. If the percentage is a decimal, yes. So you always use your percent as a decimal. So even if this were something like by 1.5%, right? I would be using 1 minus 0.015. Now that is going to be much smaller, right? 1 minus 0.015 to the 20th. 200 now. And that would only be 110.9. Okay, obviously a much smaller percentage that it's depreciating by, right? Okay. So, all right. Now, last thing I'm going to talk about with this, because Isaac asked so nicely, and he has a test over it tomorrow, is compound interest. Okay, so this is just straight decrease and increase, like growth and decay for just exponential. Okay, but so something like a savings account, not loans, I don't think, mainly it's like savings accounts, is compound interest, which means that like what I was talking about before, right, is that it's like 1.5% of this, and then you subtract that, and then it's 1.5% of that, 1.5% of that, on and on and on and on and on. But compound interest typically takes that interest, it compounds that interest at a different rate of time than just like the years. Okay, so if we do, let's say we put $5,000 into a savings account. Okay, and it's going to get 3.5% interest, compounded quarterly, which means 4 times a year, they're going to do the percentage. 4 times a year, they're going to do the percentage. So after, let's say, 5 years, how much money will be in the savings account if you don't touch it, right? Obviously, if you make withdrawals and stuff, it's going to change. So with this case, the fact that we're looking at it's compounded quarterly, but we're looking at it 5 years. So what we're really going to be looking at is like it's doing it like kind of 20 times, right? So my exponent is actually going to be 20 because it's 4 times a year for 5 years. But we still start with our principal, right, which is our 5,000. We still have our starting. Now it's increasing, so again, it's 1 plus. But here's the thing, is that 4 times a year is when it kind of builds up to that 3.5%. So that not 3.5. I'm still going to use my decimal, right? So 0.035 over 4, because it's being compounded quarterly. Okay. So I'm sorry, I may have misspoken before. It's not 3.5% every, like 4 times a year. It's 3.5% spread out over, like sort of spread out over 4 times a year, right? So 0.035 divided by 4. So that means that like every quarter they put 0.9% interest in there. That's it. And then but it builds up, right? Okay. And then to 4 times 5. I'm going to multiply that 4 by 5, because if it's accruing it 4 times a year for 5 years, it's actually going 20 times, right? Okay. So now I've got, just going to kind of simplify this down, 5,000 times 1 plus 0.035 over 4 to the 20th. So 5,000 times 1 plus 0.035 divided by 4. Boop, 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 to the 20th. $5,951.70. So after 5 years, that's a good savings account. After 5 years, you've made almost $1,000 just in interest alone. Pretty So that is compounded interest. That's exponential growth, exponential decay, all of those good stuff. No, or all of those good things. So, you guys may have been a lot of people have been asking about this calculator that I'm using. It's called NumWorks, and they are sponsoring our lives for this month of May. And there is also a sweepstakes that you can enter if you click the link in my bio, and you can enter to win a free calculator. They're great. They're so user-friendly. I cannot stress that enough. Like, my students love them. I love them. It makes it really easy to navigate the graph. You don't have to remember 14,000 different keystrokes. It's very intuitive. It's very easy to get things. Guys, it simplifies radicals for you. Like, that's huge. If you just put in like square root of 24, it doesn't just give you the decimal. It gives you 2 root 6. It's amazing. It is absolutely amazing. So.
Testing.
Yeah, I'm getting to that. So it's testing season. APs are coming up. These are great and useful for testing, right? You're looking for time, right? You need that time to go through and make sure you're able to answer all the questions efficiently and all of that. And so the NumWorks calculator is just a really efficient tool that you can use. So check out the sweepstakes link in my bio. And also, teachers, I know there's a lot of you out there, you can get a free calculator. They will send you one. Go onto their website, click the link, tell them you're a teacher. They will send you one to try out. I promise you, it is worth it. It is absolutely worth it. All right, guys, that's it for me tonight, but I will be back again next week for more Math Thursday. And if you need any tutoring or anything like that, one-on-one, click in my bio, find some time. Slots are filling up, so check it out. All right, have a good night.